All right, hey y'all, it's Miss Warcow. I'm making this video in anticipation for a potential weather day, be it virtual or whatever, for this week. Today's topic is 4.5 in Unit 4. This is covering global wind patterns. So we're going to do a couple things in these notes. Number one, we're going to review air pressure. Should be a middle school review for most of y'all. We'll talk about how air pressure affects winds. We will talk about how wind moves on Earth, how the rotation of Earth affects that. We will look at convection cells within the atmosphere, and then finally put all that together and talk about the global wind patterns. Okay, so first thing we need to do is remind ourselves about air pressure. All right, so I'm going to make my little note right here. All right, something about air pressure, all right? So air pressure is the weight of air. I need you to be okay with the idea that air weighs something because it's made out of matter, therefore it has mass, okay? And that pressure can be either high or low, okay? Don't want you to worry about actual numbers. That's not what's important here, okay? Now, with high and low pressure, sometimes this can get a little bit confusing because when we hear words like high and low, we think about elevation. So things that are low are down here and high is up here. But with air pressure, it's actually the opposite. When we say something has low air pressure, what we mean is it has low density, okay? So low pressure air is less dense, all right? Now, why is that important? Well, less dense things want to rise. Now, when we talk about air, as air rises in the troposphere, it gets cooler. All right, cold air cannot hold as much water vapor. So as air rises, it cools, that water vapor condenses, and that is going to make precipitation. So you're going to remember that lows lift and make lousy weather. High air pressure would be the exact opposite. So we don't mean high as in up here, we mean high as in it's dense. The air is all packed together. Things that are more dense want to sink, all right? And sinking air, as air sinks in the troposphere, gets closer to the surface, it's gonna get warmer, all right? And you're not gonna have condensation, you're gonna have the opposite, all right? And that's going to lead to very dry condition. High is heavy. So you remember high is heavy, air sinks, lows lift, air rises, all right? Now, what does this have to do with wind? What's this have to do with wind, okay? Air moves from areas of high pressure to areas of low pressure. Kind of like osmosis or diffusion from biology, we go from highs to lows. That's where it wants to go. All right, that movement of air is called wind. Okay, so let's take a look at an example of high and lows that you could see in one localized example. All right, I'm gonna use a day at the beach, okay? So let's take a look at that. A day at the beach, talking about air pressure. So I'm going to draw a picture. I'm gonna have some land. I'm gonna have my ocean. All right, and of course I have my little sunshine over there. So we're at the beach. All right, we're enjoying a nice day. All right, and you probably can relate to this if you've ever gone to a beach on a hot summer day. This land and this water are not the same temperature. The land heats up really quickly, all right? That's because land has a lower specific heat capacity. It gets really hot really fast. That means that this air above the land is going to be warmer, which means it's less dense. What kind of air pressure is that? If it's less dense, it's low. All right, that says low. I know there's a glare on the board. All right, so this air is going to rise. This air is going to rise. Can you see that? Yes, you can. Perfect. All right, over the water, on the other hand, all right, even though this is getting the same amount of sunshine, water has a high specific heat capacity. It's going to warm up a lot slower. This is going to stay cool. The air above it is also going to be cool, all right, or colder, which means it's more dense. What kind of pressure is more dense air? That would be that says high, everybody. That's what that says, I promise. All right, this is higher pressure. So this air is going to sink. Now we don't have these two areas just existing by themselves, all right? This is all connected. All right, so air is going to want to go from where it's high pressure to where it's low pressure. So we're going to connect these. Boop. All right. On a warm summer day at the beach, you may know this as a sea breeze. The air is moving from the ocean towards the land. But what's happening up here? All right, we got to finish this diagram. We got to finish it. All right, this is going to connect here. All right, and we're going to make this thing here. What have we made? We made a, let me write this down, convection current. Okay, anytime we're talking about highs and lows, we're going to talk about this when we talk about the cells within the atmosphere. We have a convection current going on. Warm, less dense air is rising. All right, it moves, it cools, sinks, high pressure moves towards low pressure, and it keeps going on and on, just like the convection currents in the mantle for plate tectonics. Okay, so that's how wind works. Yay us. Okay, now let's talk about the movement of wind across Earth's surface and what changes depending on where we are. So if you were here on, what is today? Today is Tuesday, by the way. I'm making this in the past. Woo. Okay. If you were here on Tuesday, we talked about ocean currents, all right? And we saw this pattern with surface currents. I'm going to draw a picture real quick. This is the Earth, this is the northern hemisphere, this is the southern hemisphere. And we talked about surface currents. They make these things called gyres, and gyres are just circles of water, okay, or like loops of ocean currents, all right? So in the northern hemisphere, gyres do this number. So warm currents move away from the equator, cold currents move to the equator. All right, and in the southern hemisphere, they do the exact same thing. Warm currents move away from the equator. Cold currents move to the equator, and that's why they cycle heat. That's why they moderate climate. All right, but you'll notice something different about these two, okay? This one in the north is deflected or rotates to the right or clockwise, okay? Whereas this one here in the southern hemisphere deflects to the left or anti-clockwise or counterclockwise, whatever you say, however you say it, okay? Why is that? Why do they always go to the left down here but to the right up yonder? That has something to do with the Coriolis effect. Okay, here's what I need you to know about the Coriolis effect. This is caused by the Earth's rotation. We live on a ball that is spinning. It spins once every 24 hours. All right, this spinning movement means that we have different rotational speeds at different latitudes. I don't want you to get too caught up in that. All right, but essentially what is happening, these are essentially going in straight lines, and you're like, that doesn't look like a straight line to me. Our target underneath is moving. Okay, so if you imagine one of those like old school like merry-go-rounds on like a playground that like you manually push or whatever, okay, and you sat on one side and your friend sat on the other side, and you try to toss a ball at them, okay, when you throw it, it's going to go in a straight line, all right, because that is the direction of the force that you applied to it, all right, that's going to move in a straight line. but it's not going to make it to your friend directly across from you if the merry-go-round is spinning. It's going to look like it veers off to the left or to the right. It's not actually veering off. What's happening is the person straight across from you, that target moves. All right. I would recommend you watch, if you go on YouTube, you can definitely find better examples of, or find a better visual for that. Okay. So with the Coriolis effect, because the earth is moving, wind and water is going to be deflected. All right. So instead of going in straight lines, like from the equator to the poles, it's going to veer off to the left or right. In the north, it's to the right. In the south, it's to the left. That's what I want you to know. That's important. Okay? Okay. So now that we have that, we have the Coriolis effect. We talked about pressure. Now let's take that air pressure. Let's blow it up on a big scale. Okay? I'm going to erase this. I'm going to keep my globe, though. And I'm going to add some latitudes, okay? So my latitude here in the middle. This is 0 degrees latitude. That would be the equator. Excuse me. This line, I'm going to do about the same. I'm going to try to make this as even as possible. This is 30 degrees south. This is 30 degrees north. I'm going to draw one more line. Pretend these are even. This is 60 degrees south, 60 degrees north, and then at the very tippity top is 90 degrees north, and at the very, very bottom, 90 degrees south. Okay? So we want to look at air pressure and how latitude impacts that. Okay? And then we're going to see how that generates these wind belts. So I'm going to start at the equator because that's the easiest one. All right? We know at the equator, we know I like how I did that instead of writing out sun. All right, at the equator, we had the most solar radiation. So because we had the most solar radiation at the equator, what kind of air pressure is that? The air is warm and less dense. It is low. Lows lift. So over here by my equator, actually, I'm going to do it on this side. So I should put the numbers on this side, but it's okay. It's okay. All right. So at the equator, air is rising. And you're like, that's going to the left. No, pretend you're standing on the ground here. Air is rising. All right, I'm going to write this here. Equator, low, air rises. And that makes sense. That makes sense. That makes sense. At the equator, we have a lot of precipitation because that air is rising, cooling, and condensing. Okay? So that air is going to move away after it's risen, cooled, and condensed. All right, it's going to flow this way. All right, and then something happens at 30 degrees. At 30 degrees, we have high pressure. So high pressure, remember highs are heavy. Air is going to sink. Air sinks back down to the surface. All right, but we remember wind. Wind wants to go from high to low. All right, so that air is going to rush back towards the equator and create a convection cell here. All right, the convection cell, I'm going to go ahead and write this down because you do need to know the name of this. The convection cells between 0 and 30 degrees latitude are called Hadley cells. Hadley cells. Hadley cells. Okay? Why are they called that? It's somebody's name. It's probably a name. All right? Now, going back to biomes just for a quick minute, it makes sense that there's high pressure at 30 degrees latitude because 30 degrees latitude is where I find dry deserts. It's where I find those tropical deserts. All right? Deserts are dry. Of course there's high pressure. Air is sinking. That's why there's no rain there. That checks out. All right? But let's extend beyond that. Let's go outside of this zone. All right? So this is a Hadley cell. All right? From 30 degrees, not only is air going to rush back down towards the equator, but it's also going to rush this way. all right, towards 60 degrees. All right, at 60 degrees, I have another area of low pressure. So air is going to rise because lows lift, and that's going to connect back and make another convection cell. All right, write this down. The convection cell between 30 and 60 degrees latitude is called the Ferrel cells. Ferrel cells? Ferrel cells, whatever. All right? Again, probably somebody's name. All right? And that leaves us with just one more thing. What's happening between 90 and 60? All right? At 90 degrees, we know that it's really, really cold because there's not a lot of solar radiation reaching those places. So here, of course, we have high pressure. Highs are heavy, so they're going to sink towards the surface, and they're going to rush to these areas of low pressure. All right, and we're going to finish off this final convection cell. Okay. So we have another set. We have another set of convection cells. Between 60 degrees and 90 degrees, we call these polar cells. All right? So here's a polar cell, polar, ferrel cell, ferrel, and then of course in the middle, Hadley cell. That says Hadley, everybody. Hadley. All right. So now I have my convection cells. Now I want to know what those convection cells have to do with global wind belts. All right. So we're going to combine what we know about pressure with what we know about the Coriolis effect. I'm going to start here in the Hadley cells. Those are from 0 to 30 degrees. All right. I know that wind wants to move from where it's high pressure to where it's low pressure. So if the Earth were not rotating, these winds would just go from the north to the south or south to north, depending on which hemisphere you were in. But we know the Earth is rotating, so we need to take that into account. So let's start in the northern hemisphere. I'm going to pretend I'm standing at 30 degrees latitude. That's me, everybody. That's me. See? There I am. Okay? I know from the Coriolis effect, winds in the northern hemisphere are deflected to the right. So I'm going to stand here. I'm looking at the equator. This is my right hand. That's my right hand, everybody. Do you see it? That's my right hand. All right? So the winds are actually going to go this way. And you might be saying, that looks awfully left. For something that's going right, it's going clockwise. If I were to keep going in a circle, that would end up going to the right. All right. Boop, boop, boop. Okay? Now let's do the same thing in the south. I'm going to stand here at 30 degrees latitude. There I am again. There I am. I packed my bags. I know that things in the southern hemisphere are deflected towards the left. So if I'm standing on the 30 degrees, looking at the equator, here's my left hand, everybody. That's my left hand, everybody. It's going to deflect boop, 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 boop. Okay? These winds between 0 and 30 degrees, those are called the trade winds. Sometimes they are called easterlies. Can everybody see that? Yes, you can. Sometimes they're called easterlies because they go from the east to the west. All right? Another thing you might see, this middle part, all right, between 30 degrees on either side of the equator is sometimes called the ITCZ. So that means between. Tropical, so between the tropics. Convergence means to come together. And then zone. All right, so this is the ITCZ because within the tropics, winds converge back to the equator. All right, that's our ITCZ. Now let's do the Faro cells. Let's see what's happening there. All right, so again, wind is going to want to go from where it is high pressure to low pressure. All right, so I'm going to move myself just a little bit. So here I am at 30 degrees north. That's where the high pressure is. I'm looking to 60 degrees north. Now, if I'm looking this way towards 60 degrees, my right hand is over here this time. Hello, that's my right hand over on this side. So these winds, instead of going like this, they're going to deflect to the right. All right, so they're going to do this number. Huh, neat. They're going the opposite way. All right, if I do the same thing down here, if I look down at 60 degrees, all right, if I'm looking here, my left hand's over here. This would be my left hand. Winds are deflected to the left. All right, and I see a little pattern. Now, between 30 and 60 degrees, these winds are called westerlies. These winds are called westerlies. Why are they westerlies? Because they go from the west to the east. This is the main wind pattern that influences weather movement within the United States. All right, this is why the west side of the Cascades are the windward side, and the right side or the east side is the leeward side or the rain shadow. Okay, that leaves us with one more. Let's just double check this just to make sure we got it. I'm going to go to the North Pole. I'm going to stand right here. All right. Wind wants to go from high pressure to low pressure. If the Earth wasn't rotating, it would just be straight to the south or straight to the north. All right, but we know it's not. If I'm standing here looking at 60 degrees, there's my right hand. That's my right hand, everybody. Boop, boop, boop. All right, and same thing. If I were standing here, upside down, that's me, I'm standing upside down. My left hand would be this way, boop, boop, boop. All right, just like in the ITCZ, these winds are also going from the east to the west. All right, between 60 and 90 degrees, we have, whoops, excuse me. We have our, that's just polar, everybody. We have the polar easterlies, okay? So, high pressure is heavy, lows lift, wind wants to go from where it's high pressure to where it's low pressure, all right? Because of differences in heating on Earth, we get different areas of high and low. Low pressure at the equator, high pressure's at 30 degrees, lows at 60, high pressure at 90. That creates our wind belts, the trade winds, the westerlies, and the polar easterlies.